If I can communicate at least as well as a tree. So it's great being here at this workshop on compositionality. Compositionality is a very broad subject. I find it fun trying to explain to friends what this workshop is about. I say it's about taking little things and sticking them together and getting bigger things. That's what the workshop is about. And let's see if I can, yes. So the kind of things I like to stick together to form bigger things of the same sort are networks. So in many different areas of science and engineering, people use diagrams of networks, which are basically little boxes connected by wires of different sorts. So a very classic example is electrical circuit diagrams, which basically most of the machines in this room have been designed by first producing a diagram of this sort and then instantiating it. But there are many others. So this is it's actually a Petri net, but being used for a model of the HIV infection by HIV, showing different states of white blood cells and the virus and how they interact. In biology, they use a lot of different graphical networks and graphical languages involving networks. In fact, they have so many different kinds that there's a committee now called the Systems Biology Graphical Notation Committee that's tried to standardize these and have come up with 3 languages that they think cover most of the things they want to talk about. So this is some interesting biological mechanism called the repressilator, where each one of these reactions represses the function of the previous one. And in control theory, which is the art of getting mechanical and electronic systems to behave in a stable and robust kind of way, they use something called signal flow diagrams. So the simplest sort of thing would be a thermostat. The signal comes in, which would be, say, the temperature of the room, and then the thermostat will affect whether the furnace is turned on, and of course then the furnace affects the temperature of the room, and you have a feedback loop, and that looping is the key idea in control theory, to try to get feedback loops to do what you want. So I've loved diagrams of networks ever since I started trying to think about Feynman diagrams in a mathematical way and trying to think about generalizing them to quantum gravity. And the relationship of them and category theory has always been fascinating to me. But now I'm trying to do slightly more practical things, which isn't saying much, really. And so I started eyeing these other kinds of network diagrams as something to investigate. And I really think we need a good general theory of these. First of all, because these different languages are developed by practitioners of different fields who aren't mathematicians, and they think of what they're doing as their own personal, or their own, the personal property of their own community of researchers, and thus they don't develop them at the level of generality that makes it easy to transfer their results to other fields. So for example, chemists have done a whole lot of work where you can look at a chemical reaction network and infer properties about the stability of the chemical reactions without having to solve a bunch of equations. And those models of chemical reaction networks also can be reinterpreted as models in other areas, like evolutionary game theory, where you have different populations interacting with each other. But because the chemical literature is all under the name of chemical reaction networks, it would take, and the terminology is all in the terminology of chemistry, it would take a somewhat intrepid evolutionary game theorist to realize that they should start reading all these chemistry papers to find these stability theorems that they could use in evolutionary game theory. Now, it's not clear, of course, that making things in the language of category theory actually eases communication between evolutionary game theorists and chemists, but I'm trying to explain things to different people in different ways, and hopefully, if enough people do that, we'll get some communication going. In this particular workshop, I somehow, perhaps erroneously, probably erroneously, thought that lots of people would know category theory, and so I could finally come out and say what I really mean. But we'll see how well that works. But at least a certain number of you are experts in category theory. and the rest of you should ask questions and things. So the idea of category, how does category theory play into this, is that networks of some particular kind, so fix some particular type of network, if you specify some input and output nodes in your network, you can think of that thing as a morphism in a category. So here I have my networks are just a graphs, just a set of vertices and a set of edges where each edge is directed. And the way I'm specifying some of the vertices as inputs is by a map from a set into the set of vertices. Notice I'm not demanding that it be one-to-one. That's a little subtle point, which you don't have to worry about too much, really. And then y is some other set which is being mapped into this set of vertices, and that describes the outputs of the network. And the point is that then we can think of this as a morphism from x to y, and then if we have a morphism from y to z, we can compose them by sticking together the output vertices of the first network with the input vertices of the second. So in a category, you can compose morphisms, and this workshop is really all about that, hence the term compositionality. In fact, this is going to give you a symmetric monoidal category, which means that in addition to being able to compose morphisms one after the other, you can set them side by side, which is called tensoring them. And that lets you discuss processes being done in parallel as well as the ones being done in sequence. So the nice thing is that networks of this sort let us describe open systems. So there's this concept of open system that I can tell already a lot of you understand, but let me just try to say what an open system is. It's a little hard to define in generality, but it's basically a system where stuff of some sort can flow in or out of the system. So stuff could be energy, information, signals of various sorts, matter. If you're studying chemistry, you may have like a vat of chemicals, but you're actually like pouring new chemicals in or pouring them out, which is what you'd be doing in a chemical production process where you're trying to manufacture some chemicals. So stuff in the most broad sense can flow in and out, and you're concerned with that fact. And then you can combine open systems by composition, that is feeding the outputs of one into the inputs of the other, or tensoring, setting them side by side. So the language of symmetric monoidal categories is the right language for discussing open systems in this sense. And what people do is they use networks, or these diagrams of networks, as a syntax for open systems, and then use the ideas of functorial semantics, which luckily Prakash already explained yesterday, to interpret those networks as and figure out their meaning. So Levere, I guess in 1963, came up with this idea of functorial semantics, and in this context, what it amounts to is that you think of networks of some particular type, like electrical circuit diagrams or whatever, as morphisms in some particular symmetric monoidal category, say X, and that will be your syntax. And then to interpret a network, we choose a symmetric monoidal functor, F, say, from X to some other symmetric monoidal category. And that category will be good for what we call semantics, or endowing meaning to the diagrams, which are the morphisms in X. So the classic examples of symmetric monoidal categories that you might use for semantics would be the category of sets and functions, or the category of sets and relations. So if you use the former, then every network, every morphism in X would get sent over to a function over here, which is a morphism in set, and the meaning of that is that we think of the interpretation of our network is that it describes a function from some input data to some output data. But very often we want to use other categories besides the category of set. Very often you might just want a relationship between the input data and the output data. The input data may not determine the output data. They may just need to obey some relation. And there are many other variants of this idea. But that's what I claim is going on in all these disciplines when people are drawing diagrams like Feynman diagrams or electrical circuits, is that secretly in mind although they wouldn't phrase it this way. They have a symmetric monoidal functor in mind, which lets them interpret the diagrams as having some meaning. And the point is that working with diagrammatic notation is more convenient often than the traditional linear symbol string notation. So how can you actually build symmetric monoidal categories with networks as the morphisms? How can you start doing this? So one way, which isn't the main way I'll be talking about, is the sort of algebraic approach using generators and relations. So the idea is that you can present, just as you can present a group by giving some generators and relations, you can present a symmetric monoidal category. So a category has some objects and morphisms. So what we do is we pick a set of generating objects. So you start with some objects, and then you build up other objects by tensoring those. So if you think of an object as a dot, tensoring it would be like putting a bunch of dots side by side. And then we also need to give a set of generating morphisms. You could think of a morphism as like a network. So you can, a generating one might be some simple network, like where two things come in and one go out. And the way we use them to generate more morphisms is by tensoring and composition. So you take those little building blocks and you start assembling them vertically and horizontally to build big, complicated networks. And then, as always in a presentation, you would want some relations. And typically here we would only impose relations between morphisms, saying that something is equal to something else. Some diagram we count it as being equal to some other diagram. So there's a nice way to go about this. And the advantage of it is that then you can describe symmetric monoidal functors between symmetrical monoidal categories by just saying where the generators go. So if you've ever studied groups using generators and relations, you know that like what do you actually do with those generators and relations? Well, one thing you do is you describe group homomorphisms to be in the following way. You just need to say where each generator goes and check that the relations that held in the original group still hold over here on the images of them. So you do the exact same trick to construct a bunch of symmetric monoidal functors like these ones that assign the meaning to networks. Now this method is a little bit, it takes a lot of work. It gives you a lot of insight if you can succeed. It takes a lot of work because often if you start with a symmetric monoidal category where the morphisms are some very simple pictures like that graph I showed you, it may not be obvious what the generators and relations are. So for example, in the case of the one that I just showed before, this plain old directed graphs, directed multigraphs to be super precise, Rosenbrug, Sabadini, and Walters came up with the generators and relations description of that symmetric monoidal category. But it took work to do that. So there's another approach, which is what I mainly want to talk to, which Brendan Fong worked out, which is using some technology called decorated cospans. So let's look at this same network that I showed before, and we'll think of it this way. For starters, it's a cospan of finite sets. So a cospan is just a diagram that looks like this, where you have two objects here, both mapping to the same object here. In this case, S is the set of all vertices of this graph, and I and O for input and output are the functions from these sets X and Y into S. So that would just so far be talking about the vertices and nothing about the edges. But the idea of a decorated cospan is that we want to take this object here, in this case this finite set S, we want to decorate it with some extra structure, which is the extra structure present in our network, whatever that may be. In this particular case, the extra structure is that we've got a graph here, not just a set of vertices. So the extra structure is to say, we don't just have the set S, we also have a set E of edges, and every edge has a source and target. Each edge here has a source vertex and a target vertex. And so what Brendan did is come up with a nice technology for constructing categories where the morphisms are decorated cospans. So you have to say how to compose them. There'll be symmetric monoidal categories, so you have to say how to tensor them. And you want to be able to do various nice things with them that are the kind of things you want to do in network theory. But I want to show you how this works, and I want to use a somewhat more interesting example than the example of graphs. So I'd like to use Petri nets. So a Petri net is just a bipartite graph, meaning that there are two kinds of vertices, which are these red circles and these green squares here. And the two kinds of vertices have names that are supposed to be evocative. So the red circles we'll call places. So we could think of those as like little bags where you could put some rocks. And then the green things we call transitions. And so the idea is here is that if I have a rock in this place and a rock in this place, they can go in, that's what these arrows mean, through this transition, something happens, and then something pops out, one thing pops out and goes into this circle here. Or similarly, one thing of this type could go into this transition and then turn into two things of this type. So Petri nets have been around for quite a long time. In fact, although they became popular in computer science as models of concurrency starting in the 70s, maybe the 60s, I'm not exactly sure, they're actually apparently invented by Carl Petri when he was a teenager in 1939 as a language for chemistry. That's what legend has it anyway. If you read Wikipedia, it says the legend is that this is the case. So I don't. That sort of makes you wonder if it's really true or what. But so here's a Petri net used for the purposes of chemistry, and they are now still used for the purposes of chemistry. And that's actually that's closer to my motivation, because I claim no knowledge of computer science. I'm more of a physicist, and chemistry is close enough to physics that I can sort of encroach on that territory without getting too nervous. So you've probably seen chemical reaction networks. You may not have noticed that those are pictures of morphisms in a symmetric monoidal category, where the objects are the different kinds of chemicals called chemical species, and the tensor product is written as a plus just to confuse you or something. And then the arrow is the name of the morphism, the going from something to something else. But in addition to that style of drawing chemical reaction networks, you can also draw them as a Petri net. And so here we have a reaction that takes a carbon atom and a molecule of oxygen, and out pops one molecule of carbon dioxide, and so on. And there's certain advantages to this style of drawing and certain advantages to this style of drawing. Theoretical chemists have all sorts of theorems about the stability of systems of chemical reactions and like whether they engage in cyclic behavior or converge to an equilibrium or whatever, based on the topology of the network. And some of the theorems use this style of network as the basis of the theorem, and some use this style. So they're both very interesting. So you can imagine, if you're trying to get a little closer to the computer science picture of things, you can imagine a bunch of little markers or tokens in each of these places at any given time, and then as time passes on, those tokens go through a transition and new tokens pop out as a way to keep track of how many atoms or molecules you have of various kind. But they're used in many other fields. So I was at a talk on AIDS, and they used this model of the infection of white blood cells by virus particles. An individual virus is called a virion. So you could have like a virion meeting a healthy white blood cell, infecting it by means of this transition beta, and then out pops an infected white blood cell, which then may emit more virus particles, or it may die, and so on. And what they do in this kind of discipline is they take this kind of diagram and then they translate it into a system of ordinary differential equations that describes, as a function of time, how the number of these various entities in your places changes with time. So this is a syntax for describing ordinary differential equations. And you could just write down the ordinary differential equations and not draw this picture, but this picture somehow makes it easier to understand what's going on, and in particular it's compositional in the sense that you can stick together these pictures to get fancier pictures, which is really a way of sticking together systems of differential equations to get more differential equations. But that's what I want to talk about. So in systems biology, they use these quite a lot. So I'm already forgetting. This is something about the operation of a muscle. They had very complicated Petri nets and many other fields they're used. Okay, so let's describe how you can get some differential equations out of a Petri net. Well, you need a little bit more information. You need a Petri net with rates, by which I mean that each transition is attached. We attach to it a positive real number called its rate constant, which somehow describes how fast or how likely it is for that transition to occur. And then from that data, we can write down a system of differential equations, which call the whole system, I'll call it the rate equation, describing dynamics. So for example, if we take this Petri net here, we get this system of differential equations. So to write that system down, I'll give names to these different places, and I will think of those names as also denoting real valued functions of time, which describe how much of that item you have. So now here I'm using A1 to mean how much of this stuff we have. And we're assuming we have got enough of it so that we're not counting atoms in an integer manner. We're just counting the concentration of a chemical as a positive real number. And the idea is that we write down this system of differential equations showing how they change with time. And so, for example, this transition here says if a thing of type A1 meets a thing of type A2, they can turn into an A3, and they do so at a rate proportional to R1. So that means these A1s will tend to disappear. They'll tend to go away, which is why there's a minus sign here. And you get minus R1, A1, A2. So they can only go away if both an A1 and an A2 are present. So in chemistry, you get this law called the law of mass action, saying that it happens at a rate proportional to the product of the chemicals that are going into the reaction. So similarly, A2 is going away by the same process. So we can see the exact same term here. And A3s are getting created by this transition. And so we see that the amount of A3s is increasing by the same rate. But then we have this other transition, R2, that takes a single A3 and produces two A2s. So that also has its effect. So A3s are going away at a rate proportional to the number of A3s times R2. So notice that's just linear in A3 because just one A3 is getting used. And then two A2s are getting created in this transition, so that's the reason for this coefficient 2. So hopefully that illustrates how it works, and that I could draw an arbitrarily complicated Petri net, label the green boxes by positive real numbers, and you could just crank out this system of differential equations called the rate equation. So that's what chemists and other people do. So this is the idea of the translation from the syntax into the semantics in a somewhat informal way, which is the way that people usually think about it. Okay, so far these Petri nets are just describing closed systems, but you can actually have open Petri nets, and I'm going to make a symmetric monoidal category where the morphisms are open Petri nets with rates, and I'll call that category Petri. So the objects will be finite sets, like the set X and the set Y, and a morphism will be a Petri net with rates together with functions from X and Y into the set of places. So, it may not be 1-to-1. If it's 2-to-1, it may be a little bit confusing, but the idea is that there could be two different kinds of things that could maybe coming from two different places that could go in here. So to compose these guys, you do a more or less obvious thing. So here I have one of them going from X to Y, the same one as before, I guess. And here I have another morphism, G, going from Y to Z. So we have a function from y into the set of places of our first Petri net, but also into the set of places of our second Petri net. And so we use that to say, hey, we're going to identify this place with this place, and we get a single place in the composite Petri net. So we just identify the outputs of one with the inputs of the next. And then you can tensor morphisms as well, just by taking one of them and another one and drawing them side by side. So you take the disjoint union of the input sets, the disjoint union of the output sets, and you set the Petri net set by side by side to get the tensor product in this category. So as I said, you get a rate equation from a Petri net. Well, an open Petri net will give something that I'll call an open rate equation, which has some extra terms describing flows in and out of the of various things corresponding to the various places here. So if I had this one here, I would get this equation. So what I'm doing now is, as before, labeling the places with functions of time, and I'm also now labeling these inputs with functions of time. And these inputs functions of time do not obey any differential equation, because the idea is that some external user could decide to dump in chemicals of various sorts at a rate that it was up to them to decide. So I1 of t, you could say, is determined from outside of the system, and not, it affects the behavior of how much A1 you have, but it's not determined by any equations of its own. And here I have I1 and I2 coming in here, so we have both of those added up, affecting the amount of A2. And then by a sign convention that's very useful, over here we put a minus sign in front of the O1 of t. We need that sign convention so that when we stick things together, it all works out nice.
The picture has an arrow going from the transition R1 back to A2, and I don't see any
you're right. That's a mistake. So there should be an extra term. Great, that's excellent. So this should have been like the test that I used to see if people were paying attention. But yeah, so there should be an extra, what?
You just put it in the wrong line. You put it in the A1 line.
Oh.
No, I think it's good.
Okay, so it's an exercise to figure out what I did. We should get A1, A2 times R1 showing up once here, so it should be plus that, but also it should be showing up twice here. Wow, I really gummed this up. So this should be A1 times A2 here. Yeah, so I don't know. This must be the slide that I wrote after a few beers or something like that. I don't know why this.
Because there's an R2, there's an R1, A1, A2 going out of A2 and also into, so they probably cancel out.
Oh, you mean that was okay? I give up. Okay, so I will fix this if necessary. I probably should have at least written A1 squared. It's sort of uncouth to write A1 times A1, even if it's correct. So hopefully that illustrated the idea by letting you all see that I didn't know what I was doing. So the Petri net part is supposed to work exactly the same as before. The only new part is these input and output terms. So that's what I was really trying to explain, and I gummed up everything else. So open Petri nets here are serving as a syntax with these differential equations, which you could call an open dynamical system, providing one possible semantics of them. So in the idea of functorial semantics, we'd like to get a symmetric monoidal functor from the symmetric monoidal category Petri to some other one, which I'll call dynam, where the morphisms are open dynamical systems. Now, computer scientists like to think about Petri nets in different ways. They don't usually write down differential equations from them. So they would be looking at some other choice of semantics, and I claim that would give you some other symmetric monoidal functor to some other category. But I'll just think about this one semantics here. So what is this category of open dynamical systems? Well, it'll be a category where an object is a finite set and a morphism is an open dynamical system. So what that will mean for me is it's a cospan of finite sets. So S you think of here as the set of all the places in our Petri net, for example. And so there could be a real number attached to each one of them that may vary with time. And to describe how it varies with time, we put a vector field on the vector space R to the S. So a dynamical system is usually thought of in modern languages as a vector field. And so an open dynamical system has that vector field on S, but this additional data, this input and output data, which is what lets us understand inputs and outputs. So the idea is that if I have an input and output flow, so an input flow would be a function of time taking values in R to the X, and an output taking values in R to the Y, and that's the wrong shape R there, then the open dynamical system would first of all would tell you how the amount of each thing in our set S changes with time. And so it would be a differential equation that, for starters, would involve the vector field on S. So if I stop there, that would be just like a classic dynamical system. But then plus some extra terms here. So the idea is if I've got a function on X, a real valued function on X, and on a finite set X, and I have a map from X to S, I can push it forward to a real valued function on S by summing the values of all points here that go to a certain point here. And that's what this subscript star means. It's push forward. So I do that, and then I subtract this. So this is just an abstract description of what I showed you in the example. So that's the recipe. So I've been working on this stuff with Blake Pollard, who is here. He's right here. And here's our theorem. There's a symmetric monoidal functor, which I'm calling box, from Petri to Dynam, which sends any open Petri net to its open dynamical system. So the main thing about this theorem is that this box thing needs to preserve composition and tensor product. So being a symmetric monoidal functor means mainly that you preserve composition and you preserve tensor product. And so what this means is that if we want to figure out the open dynamical system for a composite of two Petri nets, we can figure out the open dynamical system for each one and then compose in the category of open dynamical systems. And similarly for tensor product. So this is what compositionality is all about, determining the behavior of a very large complicated system by figuring out the behaviors of its pieces and then just gluing them together. So that's the key idea here. So the question, though, is how do you prove a theorem like this? So this is where Brendan Fong's theory comes in handy. So he has a very general, abstract way to get a hold of such symmetric monoidal categories and such symmetric monoidal functors. So we'll start with a category C that has finite colimits. Like in our examples so far, it's always the category of finite sets. Then you can build a, then you can talk about cospans in there, and you can compose cospans. And the way you can compose cospans is called taking a push out. So you should think, in the case of the category of finite sets, you should think of this as first you take the disjoint union of n and n prime, but then you identify a point in n with a point in n prime if one of them is the image of some point in y under O, while the other is the image of that same point under I prime. So that's sticking to first taking the disjoint union of two sets and then sticking them together, gluing them together. So in case you're not into categories, push out is just a fancy name for sticking things together. It's very important if you're interested in compositionality, because the composition is sort of about sticking things together. So it's known that this structure gives you not a category with these as morphisms, but something a little bit subtler called a bicategory. Because the problem is that push-out is defined only up to isomorphism, so that composition doesn't obey the associative law on the nose, it only holds it up to isomorphism. So you get a structure where you need to be able to say, you need a fancy structure to say that composition is preserved, is associative only up to isomorphism, and that's a bicategory. But I don't want to get so fancy, so I'm just going to work with a category called cospan of C, where the morphisms are isomorphism classes of cospans. So I'll be glad to answer questions about that later, but this is perhaps a little technical if you're not into this stuff. So then, to get decorated cospans, we'll pick a functor from C to set, and the idea is we will try to build a category where a morphism is an isomorphism class of cospans, where the apex, the object on top, is decorated by an element of this set f of s. So in our example of Petri nets, x and y and s are finite sets. S is going to be the set of vertices of our Petri net, and we're going to, the set of places in our Petri net, and f of s will be the set of all ways of taking that set S and thinking of it as the set of places in some Petri net. So this decoration, this element of f of s, is just the choice of the Petri net that will be in our open Petri net. Whereas the cospan tells you what the inputs and outputs are. So the question, though, is when you compose these cospans by pushout, how do you compose the decorations? How do you stick the decorations together? So suppose I have got a cospan with some decoration and another cospan with some decoration. So how do we compose them? Well, we compose the cospans by taking a pushout, which is what I already explained. And here's what we do to the decorations. So we've got decorations D and D prime living in the sets f of s and f of s prime. There will be, in this example of Petri nets, and in all the examples that Brendan is concerned with, a map from f of s times f of s prime to f of the disjoint union, or the coproduct, f of s plus s prime. So what that's saying in our example of Petri nets is that if I've got a way to make s into the set of places of a Petri net, and similarly for s prime, then I get a way to make s plus s prime, the disjoint union, into a set of places of a Petri net, just by sitting the two Petri nets together. So this function here is technically said to be the result of f being a lax monoidal functor. A true monoidal functor would say that this is isomorphic to this. In our example, this is not isomorphic to this. In other words, there are a lot more ways to make the disjoint union of two sets into the set of places of Petri net than come from doing it on each part. But we certainly get some that way. So we do have this function. And then, because f is a functor, and we have a map from the disjoint union to this pushout, we get a map from f of the disjoint union to f of the pushout. So this just says, you take your two, in our example, this just says you take your two Petri nets, you set them side by side, and then you stick them together, where the second set is the sticking together part. So in general, the theorem then is this, that if you have a category with finite colimits, so that you can do these pushouts, and you've got a lax symmetric monoidal functor, then you get a symmetric monoidal category of decorated cospans, or F decorated cospans, where the objects are the objects of your category C. The morphisms are going to be cospans decorated by an element of F of the apex. So that's the general thing that lets us get the category we want. Well, actually, morphisms are not exactly cospans. They're isomorphism classes of them. Otherwise, you would get a bicategory. So then we can apply this all over the place. We can apply this to get this category of Petri nets, which is the example I've been talking about, where the objects are finite sets. The morphisms are cospans of finite sets, together with a Petri net with rates, having S as the set of places, as its set of places. And again, just kidding, it's actually an isomorphism class of these things. So a morphism in here just looks like what I've been talking about, one of these kind of gizmos.
What is an isomorphism class of Petri nets?
See, that's the trouble. If you joke too much, people start wanting to know what the joke means. So how about if I say afterwards what that is? I need to start drawing a little diagram to draw an isomorphism. I'll be glad to do it, but it's just some pathological honesty that makes me put this in the first place, and I'm regretting it. So you can use the same formal method to get the category of open dynamical systems. Now you take the objects to be finite sets, and you take the morphisms to be cospans of finite sets. Now, though, the apex here is decorated with a smooth vector field on R to the S. So you can again check using Brendan's theorem that you get a symmetric monoidal category this way. And I'll skip past the joke that time so you don't ask again. And so how do you get a symmetric monoidal functor, which is this providing the semantics to our open Petri nets? Well, Brendan has kindly provided a theorem for that as well. So now, suppose you've got two decorated cospan categories. How do you get a nice functor from one to the other? So you have a category with finite colimits and two different lax symmetric monoidal functors, F and G, which will thus give us two different decorated cospan categories. Well, there's a thing that likes to go between lax symmetric monoidal functors, which is called a monoidal natural transformation. And so if you have one of those, then you get a symmetric monoidal functor from F decorated cospans to G decorated cospans. So this is the power of abstract nonsense coming in here. Those of you who are into categories will just say, yeah, this is just how it's bound to go. But it takes work to prove it. But once you prove it, then you get all sorts of things without further pain. So what Blake and I wanted was this symmetric monoidal functor from Petri nets to their dynamics. And so that just follows as one of millions of corollaries of Brendan's general result. And so that you can do this not just for these open Petri nets with rates, but many other kinds of networks. So let me just list a few different kinds of things we've been looking at. So what I'm trying to do now is sort of roam around the landscape of different disciplines that use diagrams to describe complex systems and see what mathematical framework is the right one to fit them in. I don't really want to try to force them into some framework that they don't want to be in, but if they're happy to be in the framework of decorated cospans, then I'll count that as a check on my little notebook as a success. So before we got into this open Petri nets, which involve nonlinear differential equations, we started, Brendan Fong and I started looking at electrical circuits, which involve linear differential equations. And here I'm drawing the simplest kind, just involving resistors, which you don't really have differential equations at all. You just have linear equations relating the currents and voltages of the system. So we all understand, everyone who cares about electrical engineering understands about circuits made of resistors, but what we're focusing on here is the fact that we could have inputs and outputs and that we could compose these and tensor these. So we get a symmetric monoidal category of circuits made of resistors and then more generally of other kinds of circuit elements. In this paper we're focusing on passive linear circuit elements, so we have things like inductors and capacitors as well. Then all three of us, me, Brendan, and Blake, teamed up to do something similar for Markov processes. So Markov process will have a bunch of states and then rates for something to hop from one state to another state, which you could think of as a random diffusion process. And so we define a concept of open Markov process where stuff can flow in or out from the outside, and then these open Markov processes can be composed and tensored. So we get a symmetric monoidal functor here, and again, a symmetric monoidal category here, and again a symmetric monoidal functor that provides the semantics to this syntax, to these pictures here. And then my student Jason Erbley did his thesis on categories in control theory, and Pavel Sobocinski has also worked on that, and Brendan Fong has worked on that, and his thesis is actually the best place to sort of get a broad overview of going on at this point in time of these decorated co-span categories and their applications. And so the idea here is that people in control theory like to draw diagrams like this where signals, meaning real valued functions of time, move along these sort of metaphorical wires, and then various things can happen to them. They can get added, which is these black triangles. They can get duplicated, which is this little delta thing here. They can get integrated as a function of time. They can get multiplied by constants and so on. This picture here is a picture of what happens when you have an upside-down pendulum on a cart, and you can apply a force to the cart, which is this input, and then the output variables are the angle of the pendulum and also the position of the cart. And so control theorists use these diagrams a lot, and they can study the stability of various kinds of systems by messing around with these pictures and the differential equations that these pictures are a kind of code for. And so they, however, don't seem to ever talk about the fact that these pictures are morphisms in a category, and so that's what this recent work of various people has been pushing. So in fact, we get a lot of examples of network languages, that is, different kinds of symmetric monoidal categories, and then various symmetric monoidal functors between them. So the one I talked about in this talk was just this box functor assigning the dynamics to any open Petri net. But you can go further. For example, if you're interested only in steady states, that is, situations where you hold the concentrations of the inputs and outputs fixed and try to see what and look for solutions of the differential equations that are time independent, there will be typically some relation that is imposed between the concentrations and flows of the chemicals at the inputs and outputs. So you get a relation from a Petri net that describes the steady state solutions. And so that's a further simplification of the description of what a Petri net is doing that's only good for telling what's going on in if you're only interested in time-independent solutions. So that's a further symmetric monoidal functor that Blake and I have worked out. We had worked out Markov processes, but actually Markov processes can be seen as a special case of Petri nets where every transition just has one input and one output. So this category here is embedded in this one. There's a way to reinterpret circuits made of resistors as Markov processes where you think of the resistance as the reciprocal of the rate for something to go either way across a wire. So you get certain Markov processes where the rate to hop this way is exactly equal to the rate to hop that way. So you get a subcategory of Markov processes, which are really the circuits made of resistors. And circuits made of resistors are a special case of all sorts of other circuits. Here, maybe I just mean these passive linear circuits that Brendan and I studied. And either for Markov processes or circuits, you can construct a signal flow diagram. So in control theory, they use both circuit diagrams to describe how they'd actually build an electronic analog machine, but also signal flow diagrams to more abstractly describe how some signals are transformed to other signals. So the signal could be either a current or a potential when you think of it as coming from a circuit. But then you can go further and you can actually, this is what Jason, one of the main things Jason did is he studied how these signal flow diagrams that the control theorists use actually give rise to systems of differential equations. They're systems of differential equations which are linear and they're time invariant. So engineers use the Laplace transform to rewrite them as algebraic equations, linear equations over the field of functions where you take complex numbers and throw in one extra variable. So these are rational functions in one variable. This z is the Laplace transform variable. So if you look at things in control theory, they love Laplace transforms and they always work over in that context. So this describes the behavior of a signal flow diagram in the way that control theorists like. But then you can take the steady states of any signal flow diagram, and you get a relation that just describes what's going on as things are unchanging with time. And so we have this commuting diagram, maybe commutes up to a natural isomorphism, that relates all these different languages that people have looked at. So I think this is just a piece of a much bigger puzzle. There are lots of diagram languages that I haven't gotten into, but this is sort of like a indication of what I'd like to do, which is to take these different languages that various communities have developed, and they don't tend to think of those languages as mathematics. They tend to think of mathematics as the stuff that they learn over in the math courses, and these diagrams as the stuff that they need to do because to actually get stuff done. But in fact, those diagram languages, I think, really are mathematics, and they deserve to be treated with respect because they're very useful pieces of mathematics. So useful that non-mathematicians just had to go out there and invent them themselves. And so I think category theorists are in a good position to appreciate how these different languages fit together into some bigger structure. And I just want to understand that structure, which you could say is like the whole story of compositionality in all these different disciplines. Okay, so I'll stop here.
Thank you. I'm curious, why is there not an arrow from sig flow to dynam here? Is it just not been?
No, that's a great question. There is. I just had never thought about that. So when we're down here, we're only studying the relationship between inputs and outputs of the system, none of the stuff going on in the middle. The dynamical system that I got from a Petri net is describing the dynamics not just of the inputs and outputs, but also the amounts of stuff in the middle. Signal flow diagram does have the potential to do what you're saying, because the signal flow diagram shows, in addition to just the inputs and outputs, there are all sorts of other variables in the middle. So you're right, we could get a dynamical system out of it. It would be especially nice kind that would be linear. But that's great, thanks.
In addition to perhaps giving the scientists a general abstract way of presenting what they already know, can you give them any added value from this?
Well, see, that's the curse of being a category theorist, is that in addition to clarifying everything that everyone's doing, can you actually help them out? Well, so a true category theorist believes that actually clarifying things actually does help people out. So you could ask, so what did set theory ever do for electrical engineers? Well, I think it actually does something for electrical engineers to know that they're dealing with sets. It may not, suddenly make a new kind of light bulb, but it helps them. Now, I would like, of course, to give more answers that would satisfy you more, but I also just need to push back against that type of question, because the way I think of this is that it's providing infrastructure to see that all sorts of different things are related. And so when you say that, in addition to saying to scientists what they already know, you have to realize that there are lots of scientists, and they don't all know the same things. So the example that I like the most so far is the one I mentioned early on, where it turns out that the chemists have these wonderful theorems that allow you to deduce the uniqueness of an equilibrium of a system of chemical reactions just by looking at the topology of a chemical reaction network. But those chemical reaction networks can be interpreted as Petri nets. And so those Petri net models are also used in other subjects like evolutionary game theory or the HIV and so on. And so those people would never have thought to look in the chemistry literature for results on them. So I would be perfectly happy if I just wrote a textbook that said, here's how networks work, and then have tons of examples from all subjects, and then it would start people talking to each other, and then they'd start trading theorems. Now, of course, I also want to prove my own theorems that they'll all like, but that's another chance.
There's at least 6 people. Let me take them.
Okay, sorry.
So this
Sorry, no, I'm happy to let you be in charge of that.
Not just a
Just a
little.
quick comment on that.
Uh-huh.
So because I come from an engineering background, we can usually salvage diagrams in different ways to solve our problem when we have one-dimensional problems or ordinary differential equations. But we completely, I haven't seen anyone being able to generalize this to higher dimensional types. So I think that would be extremely valuable to give a tool that that seamlessly generalizes, and you can actually do partial differential equations with that. And I probably think you would go to higher categories and generalize all of these things, which seems possible.
Yeah, so I've tried to temporarily shy away from higher categories to see what I can do with one hand tied behind my back and only using symmetric monoidal categories, because there are so many of these diagram languages where the parts are basically one-dimensional, that is just bit boxes and wires. However, we had discussed this a little bit before. When you're studying partial differential equations using finite element methods, these little grids or cells that people use, you should really think, if you want to use this categorical way of thinking of them, you should be really using higher categories of some sort. And yeah, attempts to squash that into the one-dimensional language, which people have sometimes made, I think are a little artificial. So I think there's a lot of room there. That's right, for higher category theory.
Yeah, I mean, so it could be that one way of sort of addressing the point that you were pushing back on earlier is that, so you've got this very nice way of not just of describing these various network languages, but of working with them compositionally, meaning you can take descriptions of systems and glue them together. And I think often that isn't something that's standardly done in those various disciplines.
That's
People
right.
sort of monolithically describe a particular system and then go on and describe another system.
Exactly.
If one could find telling examples where actually the gluing together itself became, part of was a better way of doing some design, I think that could actually have a direct impact in terms of people actually.
Yeah, that's right. It's somewhat amazing to me that the control theorists who are always drawing these signal flow diagrams, I've never, not an expert in the subject, but in the introductory textbooks, they've never seemed to discuss composing these diagrams. They have all sorts of properties that you calculate from these diagrams, like the stability, the controllability, the observability of the system. So one thing we're starting to try to do is to look at how those properties behave under composition. And another example is the chemical reaction network literature, deriving properties of chemical reactions from the topology of the network. We're starting to look at how those behave under composition. And so that's bound to be important if you can get any results of that sort.
In the diagrammatic method here, it's saying the passage from Petri to dynamical systems, is it obvious that those partial differential equations always have solutions? And does the diagrammatic organization help in setting up the numerics to actually finding out what's going on in the system?
They don't always have globally defined solutions. You can make a Petri net where say, 2 things of a type come in to a transition and 3 of the same type come out, and that would give you super exponential growth, like dx dt is x squared, and that could blow up in finite amount of time. So of course, in chemistry, that would violate conservation of mass. So there are reasons why that doesn't. There are reasons why that doesn't happen, and you can study reasons why in reasonable Petri nets you do have global existence in time. I think it's really open to the extent to which compositionality can let us better analyze the behavior of these differential equations. But I think there's got to be something there. So for example, the human body, from one simplification of it, is like a huge network of chemical reactions going on that are influencing each other. And you have things like certain reactions are known, which act as clocks, which display periodic behavior, which then regulate other activities. And trying to understand the whole thing all at once is not the good way to do it. It can't be that that's how that's the best way to understand things. You want to understand things sort of in components, portions of the big chemical reaction network, and how those portions affect other portions. To some extent, that's what biologists are already doing. Someone's studying this reaction, someone's studying that reaction, someone may be studying how this one affects that. But I think it's wide open in terms of the mathematics, how you can prove some theorems about how the dynamics of a very complicated chemical reaction network can be how qualitative properties can be determined from qualitative properties of the parts. It's very often qualitative rather than numerical solutions that you're interested in, like does something oscillate or not?
Yes. John, where do quantum circuits fit into this picture?
Another thing I renounced temporarily was any work on quantum theory. I spent a lot of time thinking about quantum theory and also about higher categories, and I decided to temporarily turn a new leaf. So they fit in here, okay, but I'm sort of avoiding thinking about that right now.
Two more quickies, Foki.
No, I'm passing.
You're okay, we'll go then.
There is just a comment and a question.
Uh-huh.
There is a model which is called chemical abstract machine. I don't know if you have heard of that.
I've heard of it. I'm forgetting right now.
Essentially, Petri Nets as a basis, and which has been used a lot of times to describe the semantics of process algebra. Mm-hmm. But it has a couple of additional features, which I'm not sure how they could be modeled within monoidal categories. Essentially, they have a notion of membrane, which you can restrict a particular class, and another which is freezing heating. You can have parts which can disassemble or reassemble according to an equation which explains that. So this is something which is not clear to me how it would work. Then later on they introduced something which is called the reflexive chemical abstract machine, where you have even the possibility of dropping in the broth, let's say, new rules.
Uh-huh.
So you are reflexive,
Yes.
and this has been used to give the semantics of joint calculus, which is the concurrent Petri Net version of pi calculus. So those are also additions which are not trivial.
Uh-huh.
It would be nice to see if you can, in part, use readapting existing another category, or if you have to do something relatively very more complicated, like getting a closed version, for instance, of the monoidal category.
Yeah, I'm going to try to get into the more sophisticated kind of Petri nets and analyze them from this point of view, because Blake and I are involved in a project with a company called Metron, where they actually use a graphical language for designing complex systems, and their language is essentially Petri nets, and we've been sort of recruited to help think about that more mathematically. And in terms of what you're talking about, membranes, so Gordon has some very nice work on containers. So the idea that although the human body is a bunch of chemical reactions, we're not just a single undifferentiated vat of chemical reactions. There are many membranes within membranes, and reactions occurring within the regions bounded by membranes, and specific rules for how things can pass through membranes. And that's another direction I'd really like to go, to get towards more biologically realistic systems.
To restriction, the operation of restriction that you have in some languages, in which you hide a particular variable, and all the terms which use that particular variable.
I'll have to think about that. That's a little bit.
Okay, well, thanks for the discussion.